Welcome to Lecture 11. At the moment, we're developing theory that will allow us to apply the machinery of generating series to counting problems involving sets of strings. Regular expressions, which we learnt last lecture, are the first part of that theory. This lecture, we'll learn that not all regular expressions are created equal, and in fact, only some of them are any good for using with generating series. The property that makes some regular expressions useless is called ambiguity, and that's what we'll be covering today. The essential problem we'll be contending with is that regular expressions can produce strings in more than one way. The first way this can happen is with the cup symbol. Here I have a regular expression which is the cup of two smaller regular expressions, and both of those smaller regular expressions can produce the string 101. So in the original regular expression, we can think of the string 101 as being produced twice. This can also happen with concatenation. If I have the regular expression 1 cup 10 concatenated with 1 cup 01, then that will produce the set 11, 101, 1001. But when we're computing this set, we produce the string 101 in two different ways, because there are two ways of getting 101 as the concatenation of a string in the first set and a string in the second set. A different way of saying this is that the sets 110 and 101 have a Cartesian product that is quite different from their concatenation product. In the Cartesian product here, the pair 101 and the pair 101 are different, but they both correspond to a single element of the concatenation product. Here's another example with stars. The star of the regular expression 1 cup 101 cup 0111 produces the string 10111 in two different ways, as you can see here. You can get it by gluing together two elements of the set, or by gluing together three elements of the set. Here's a final example where cups, concatenations, and stars together conspire to produce a string in two different ways. From our perspective, all these examples are bad. We don't want regular expressions that are capable of producing the same string in two different ways, as this will cause problems with the machinery of generating series. A regular expression which produces each string in at most one way is called unambiguous. Otherwise it's called ambiguous. All the examples we've just seen are therefore ambiguous. To talk carefully about ambiguity, I'm going to use a piece of notation that doesn't appear in the notes. What this is a function which takes in a tuple of strings and maps them to a single string, and it does this just by forgetting the punctuation. I can write down a definition, but you should see the idea from these two examples. I said last lecture that the set 01 star is essentially equal to the set of all binary strings, just forget the punctuation. We can now make that statement more formally by saying that alpha gives a bijection between 01 star and the set of binary strings. When we saw a regular expression earlier that produces the same string in two different ways, that corresponded to an example where alpha failed to be a bijection. If A is the set 101 and B is the set 011, then alpha doesn't give a bijection from A Cartesian product B to A concatenation product B, because there are two elements of the Cartesian product that map to the same element of the concatenation product. This gives us a more formal way to understand when a regular expression is ambiguous. This is stated in the notes as lemma 3.9, but another way to see this is as a recursive definition of ambiguity. The three simplest regular expressions, epsilon, 0, and 1, are all unambiguous. Beyond that, everything is recursive. If R and S are unambiguous regular expressions that produce sets pink R and pink S respectively, then the cup of R and S is unambiguous if and only if the sets pink R and pink S are disjoint. Or equivalently, there is no string that's produced by both R and S. The regular expression RS is unambiguous if the map that forgets punctuation gives us a bijection from the Cartesian product of pink R and pink S to the concatenation product of pink R and pink S. This is saying that there is no string you can get in two different ways by gluing a string in pink R to a string in pink S. Finally, the star of a regular expression R is unambiguous if the forgetting punctuation map gives a bijection from the union of all the non-negative Cartesian powers of pink R to all the non-negative concatenation powers of pink R. This is saying that there is no string that you can get in two different ways by gluing together a collection of strings from pink R. I'll repeat that for all three of these last points, it's important that R and S themselves are unambiguous. If a regular expression contains an ambiguous regular expression, then it itself is ambiguous. To very briefly reiterate what's on this slide, a regular expression is unambiguous if all the unions it gives are disjoint unions, and all the concatenation products that it gives are in bijection with Cartesian products. In this course, when arguing that an expression is unambiguous, we tend not to use the previous lemma directly, and instead to use the first definition I gave, which is a little more informal. A regular expression is unambiguous if it produces each string in only one way. For instance, the regular expression 101 is unambiguous because it only produces one string, 101, and it only produces that string in one way. For exactly the same reason, any regular expression which just consists of zeros, ones, and epsilons will be unambiguous because it just produces one string in one way. To jump to the opposite extreme, this next example produces all binary strings, but it still does so unambiguously. Since every binary string can be obtained in exactly one way by gluing together pieces that belong to the set 0, 1, it follows that 0 cup 1 star is a regular expression which unambiguously produces all binary strings. This last example produces some binary strings, but still does so unambiguously. 0, 0 star produces all non-empty strings of zeros, and 1, 1 star produces all non-empty strings of ones. So 0, 0 star, 1, 1 star will produce all strings that consist of a non-empty string of zeros followed by a non-empty string of ones. The reason why this is unambiguous is because if I gave you a string that has this form, there is only one way you could have got that string from this regular expression. If I gave you 5 zeros followed by 3 ones, you would have been forced to take 0, followed by a 0 to the power of 4, followed by a 1, followed by a 1 to the power of 2. Those numbers 4 and 2 are uniquely determined by the example I gave you, and they will be in any other similar example. This means that there's no string that can be produced in more than one way by this expression, so the expression is unambiguous. There's a small point to clarify here on how the syntax of regular expressions works. When I wrote 0, 0 star, I meant 0 followed by the star of 0, as opposed to the star of 0, 0. In general, the star operator only applies to the symbol right before it, unless parentheses indicate otherwise. In this course, we won't be particularly concerned with looking at some complicated regular expression and deciding whether it's ambiguous or not. Instead, we just want ways to build useful unambiguous expressions. This next lemma gives one of them. It says that 0 star, parentheses 1, 0 star, star, unambiguously produces the set of all binary strings. What I'll give isn't quite a proof, but is more a sketch of a proof. We'd like to argue that this regular expression produces each binary string in exactly one way. Writing all the stars in terms of dot dot dots, we can see that the strings produced by this regular expression will look like the following. A string of M0 zeros, followed by a 1 and M1 zeros, followed by a 1 and M2 zeros, and so on, followed by a 1 and then MK zeros. Here, the dot dot dots of zeros correspond to the 0 stars in the regular expression, and the other dot 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 that separates parentheses corresponds to the outer star in the expression. The value of k and the value of all the m's can be any non-negative integers, since stars allow any non-negative number of copies of what they apply to. Now we'd like to argue that every string can be written in this way exactly once, and it's not too hard to see that this is true. If you give me any binary string sigma, then I can let k be the number of ones in sigma, I can let m0 be the number of zeros in sigma before the first one, m1 be the number of zeros in sigma between the first and second ones, and so on, and I'll get a description of sigma in exactly the above form. Moreover, if I chose different k's or different values of the mi's, they would give me a different string, so sigma is uniquely describable in this form. Therefore, the expression produces each binary string exactly once, so it unambiguously produces the set of all binary strings. Here's what we've just shown. 0 star, 1 0 star star is an unambiguous expression that produces the set of all binary strings. This is just one expression, but from it we can derive a large number of different expressions that unambiguously produce interesting subsets of the binary strings. For instance, if we change the 1 0 star inside the parentheses to a 1 0 0 0 0 0 star, then we get an expression which unambiguously produces the set of all binary strings in which each one is followed by at least 4 zeros. To see this, I would encourage you to expand this expression like we did the one on the last slide and see what set of strings it gives you. Another trick we can play when we have an expression which unambiguously produces all binary strings is swap the zeros and ones in that expression. By the symmetry between zeros and ones, that also gives an unambiguous expression which produces the set of all binary strings. To prove this, we would simply swap all the ones and zeros in the original proof. The reason we might want to do this swapping is because after swapping, it can sometimes be easier to modify the expression to describe the set of strings we're interested in. If I was interested in the set of all binary strings in which each zero is followed by at least 4 ones, then it would make more sense to work from the regular expression in the last example than the one in the first. And now we move to a regular expression which is even more complicated, but even more useful for unambiguously producing the set of all binary strings. The notes call this proposition the block decomposition. It really gives us two regular expressions, but they're almost the same. You get from one to the other by swapping zeros and ones. So to prove this proposition, we only need to prove it for one of them. Again, the proof of this proposition is a little more of a sketch. I'm going to show that if you look at the set of strings produced by this regular expression, then you'll get the set of all binary strings, and each binary string can only be described in one way as an element of this set. There are a lot of stars to unfold here, but if we unfold them all, then this is what we get for the set of strings produced by the regular expression. We get a string of B0 copies of 0, followed by a string of A1 ones and a string of B1 zeros, followed by a string of A2 ones and a string of B2 zeros, and so on, followed by a string of AK ones and BK zeros, followed by a string of AK plus 1 ones. Here, K is any non-negative integer, B0 and AK plus 1 are both any non-negative integer, but the A1 up to AK and the B1 up to BK have to be positive integers. This is because in the internal parenthesis we have 1 1 star, which produces any positive number of copies of 1, and 0 0 star, which produces any positive number of copies of 0. Here's the expression again. We'd like to show unambiguity, so we'd like to show that every binary string can be described in exactly one way in this form. I claim that this is true, and I'll tell you why, but it's probably useful to pause right now and try to convince yourself this is true. Look at a number of examples of strings, and convince yourself for each of the descriptions that that description was unique. Here's how you describe an arbitrary string sigma in the above way. B0 is going to be the number of leading zeros in the string sigma, which means zeros that occur before any of the ones. AK plus 1 will be the number of trailing ones in sigma, which is the number of ones that occur after all the zeros. Both B0 and AK plus 1 are allowed to be 0, because maybe sigma begins with a 1 or ends with a 0. After you've removed all the leading zeros and the trailing ones from the string, then A1, B1, A2, B2, and so on are simply the lengths of the blocks of what's left. I'll define the word block formally on the next slide after giving a couple of examples. Here are what the A's and B's would look like for a couple of concrete examples of strings. Again, to figure out the A's and B's, I count the number of leading zeros, trailing ones, and then the lengths of the blocks in what remain. If you're not comfortable with this yet, look back at the general description on the top of the last slide, plug in the green values of B's and A's that I show you here, and see why they give you these strings. Again, the word block, which hopefully means something to you intuitively already, is useful here. The formal definition is that a block of a string is a maximal substring consisting of zeros or ones. For instance, the first example here has 7 blocks, and the second example has 3. This regular expression we looked at produces each binary string by splitting it into blocks. Here's the statement again of the block decomposition proposition. It says that both of these two expressions unambiguously produce the set of all binary strings. The reason we put up with a regular expression that looks so complicated is because it's easy to tweak this expression to give expressions that unambiguously describe a large number of interesting sets of strings. Say we want to produce the set of all binary strings in which every block of zeros has even length. We can take the block decomposition, which shows you where the blocks of zeros are, and change all the pieces that describe a block of zeros to pieces that describe an even block of zeros. Say now that we want to describe the set of binary strings that do not contain 111 as a substring. None of the methods we've seen in this lecture or the last work to describe the set apart from this one. A string fails to contain 111 as a substring if and only if all its blocks of ones have length 1 or 2. So we take the block decomposition, we replace all the parts that describe a general block of ones with a block of ones of length 1 or 2, and we get an expression which unambiguously produces the set we're interested in. Both these examples are unambiguous for exactly the same reason that the block decomposition itself is unambiguous. We've seen a lot about strings in the last 2 lectures, but we haven't solved any counting problems yet. Don't worry, we're almost there. Now we know what unambiguous regular expressions are, we'll see next lecture how to turn them explicitly into generating series that magically solve the counting problems we care about. To summarize this lecture, we saw that a regular expression is unambiguous if each string it produces is produced in only one way. We saw 5 different examples of unambiguous regular expressions that produce the set of all binary strings. And we saw how to tweak these 5 expressions, especially the last 2, to give other regular expressions that unambiguously produce certain interesting sets of binary strings. These are the sets of strings that we'll learn how to count in the next lecture. Thank you for watching.